introduction, but now we need to go into the math, right? Very rigorously. So, you are given a state in the C4 basis, C4 space, right? The question is, can you, I don't know what happened to my pen, can you decompose it into the tensor product of two C2 space vectors. Okay, that is like this. Psi, can I write it as X tensor product Y? Okay. If you can, then it is not entangled. If you cannot, then it is entangled. Now, what is the meaning of a vector in a C4? How many qubits do you have? Two, right? Because it's a C4 space. So it must be formed by two smaller C2 space. But it's a vector in the C4 space. Can this vector be just represented by the tensor product of two vectors in the smaller space? Okay? Now, earlier I told you any, for example, this can be C4, right? Any vector in the higher dimensional space can be decomposed into the linear combination of the tensor products of the lower space. So definitely, right? Both of them are C2. Right? You can always decompose because this is how you construct. But now we're asking is only one tensor product, which means n equal to 1 in this case. Do you see what I mean? Instead of x tensor product y plus a tensor product b plus c tensor product d, can you decompose the vector only into a simple tensor product of two vectors? Okay? Still confusing, right? Let's look at the example first. Let's look at an example that is not entangled. Okay? For example, I have this vector. Can you tell me if I write it in the bracket form, what is this? How do I write it? I write it in the column form. In bracket form, what does it mean? How do you write in the bracket form? No, this is a column vector, right? In the base, in terms of, that's why I write them in terms of the basis. Okay, so it is 1, 0, and then minus 1 plus 2 minus 3. Is this okay? Let me make it clearer because I want to do tensor product. I'm going to write it as 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. Okay. But do not forget, what is 0, 0? It's 0 tensor product 0, right? So let me just spend some more time to write this out. 0 tensor product 0 minus 0 tensor product 1 plus 1 tensor product 0 minus 1 tensor product 1. Now, if I do this, then you will find that this is equals to this also. See if you agree. If you are a first grader who came into this class and see this, not first grader, fifth grader or what, came into this class and see this equation, the first grader is not going to say this is wrong. He or she only laugh at me, say, why you put a circle on the multiplication sign? That's it, right? Because this is exactly what they learn about distribution law. Right? And that is the distribution law of tensor product. So for you, you know something called tensor product. It's just another operation. This is a factorization of tensor product. 0, you can distribute with 0, 0, negative 0, 1, right? 1, 0, negative 1, 1. Is that the correct? And I know that this one represents the first qubit, this one represents the second qubit. Are you confused? The second one is 1 qubit, am I right? Why have 0 minus 1? Is this 1 qubit or 2 qubit? There is 1 qubit. Then why I have 0 and 1? This excellent. That's just the state of the qubit, just a superposition of the basis state. Sometimes I will get confused when we are sleepy, right? Then you remember this is just a state. Okay, it's just a superposition. This still represents 1 qubit. First qubit tensor product the second qubit plus first qubit tensor product the second qubit. And I can do distribution law becomes first qubit tensor product the second minus first tensor product the second, all this thing. Right? So isn't that the fifth grader will further tell me that besides that I have extra circle, I can further do this. Am I right? Because this one is common to them, right? I can factorize this out. So again, this is the first qubit, this is the second qubit. What the fifth grader might not know is that he or she cannot put this one in front. For the regular multiplication, you are okay to put the second term in front. But here you must put it at the back. Because we need the order. Our order is the first qubit go first. Now you cannot certainly put it at the bottom, at the end, when you're writing the equation, right? Because in this whole process, we implicitly actually saying that this is 1, 2, 1, 2, 1, 2, 1, 2, and this is 1, 2, 1, 2, and that's why this is 1 and this is 2. Okay? We just don't write it because we are adult, we track it very well. Make sense? Now, is this entangled, this state? No, because it's just a tensor product of two fundamental states. I mean, two states in the lower space, from the first space and the second space. Right? Exactly what it says here. If I can represent as psi equal to x tensor product y, it's not entangled. Okay? Yep. Now, we can be more specific because these are not the valid state yet. I need to normalize that. The real state is square root 0 plus 1 times square root 0 minus 1. because they need to be normalized. This is X and this is Y. Okay? Make sense? So the state is actually 1 over square root 0 plus 1. And what is this state, by the way? 1 over square root 0 plus 1. What do we call this also? The plus state. This is the minus state, right? So basically, we prove that this guy is just equal to X times, plus tensor product minus. But the plus in the first space and the minus in the second space. Okay? The plus of the first electron, the minus of the second electron. Okay? Yeah.
So in this equation, we're not up to say which state is associated with the first, this is associated with the second. Well,
Yeah.
How do you know a priori that that is the way it is?
Oh, you need to decide yourself. Yeah, you just say that this is the first electron, this second electron. You need to decide at the beginning. Yeah, and never swap it. Okay?
Okay, but if I was, maybe this is stupid, but if you were to say this is the first qubit and this is also the first qubit, that would be.
No. They come from different space. You can say this is minus 1 qubit. You definitely cannot say they are the same qubit. Yeah. Now you can call this 1, this 2 is also okay, but they are not the same. Then we look at some very important state called the Bell state, which you already did in assignment 1, right? But you didn't need to know it at that time. So we say that a C4 is just a tensor product of 2C2, right? So a regular basis, the so-called regular, you just said you don't go to deep natural basis. Maybe you call it natural basis. I don't know what people call it. Naturally is what are they? 0, 0, 0, 1, 1, 0, 1, 1, because they are the basis that you just do a tensor product of the basis state of the lower dimension, right? Very natural. This is the basis that you have, right? Now, there are some states, we call it Bell state, right? Which need to know the name. This is very important. They can find the basis. They also span the C4 space. They are complete. They can span the every vector in the C4 space, okay? And what are they? The first one is the phi plus, which is this, 1, 0, 0, 1. Phi minus, also very easy, 1, 0, 0, negative 1, because it's minus. Psi plus 0, 1, 1, 0. Psi minus 0, 1, negative 1, 0, right? You saw this in the homework one already, right? And they are all entangled. Now just ask you, when I write this psi minus as 0, 1, negative 1, 0, I represent it already in a basis. Which basis am I using when I write it as 0, 1, negative 1, 0? Which basis? What is the meaning of this 0? 0 component of what? 0, 0. Very good. Right? So I hope you understand this is 0, 0, 0, 1, 1, 0, 1, 1, right? I'm representing that, right? If I want to represent this psi minus, I need to, otherwise I don't have to represent. I just have these 4 bases, and this 4 base has some properties. And they are all entangled, okay? Let me prove to you. For example, let me prove that they are entangled. I only prove one of them. Okay. For psi, for 5 plus, which is 1 over square root 2, 1001. Now I'm going to write it as in the bracket notation. In a linear combination of the bases. What are they of the regular bases? How do I write it? 0, 0, then 1, 1. How about 0, 1, and 1, 0? Where are they? They have 0 coefficient, so they disappear, right? Assume it is not entangled. Assume it is not entangled. Then I can write this as, maybe let me call it, A0A, A00 plus A1, 1, tensor product, B00 plus B1, 1. Do you agree what I'm saying? This is X, this is Y. Right? If it is not entangled, then of course I can write it as a tensor product of 2 vectors, right? In the lower space, in the C2 space. Any questions? Now, if I can write them, then of course I can further expand it. This equals to A0, B0, 0, 0. Right? Just a multiplication. Again, the 5th grader can do it, except that you need to treat the tensor product as a regular product, right? Plus A0, B1, 0, 1. Plus A1, B0, 1, 0. Plus A1, B1, 1, 1. A0 times B0, 0, 0. A0, B1, 0, 1. A1, B0, 1, 0. A1, B1, 1, 1. Is that okay? Just a regular multiplication. Yeah. This, I'm sorry. This one is the given. All of them are entangled. But now I'm trying to prove one of them that they are entangled. How do I prove it? I prove that assume it's not entangled first. Let me do assumption. And I prove by contradiction. Okay, I assume it is entangled. If it's entangled, I have this, right? But they are the same. So what does it mean? It means A0, B0 equal to 1 over square root 2. How about A0, B1 equals to what? 0. Because we are equating the coefficient. The 0 should have the same coefficient, right? Okay. How about A1, B0? What do you get? 0. A1, B1, what do you get? 1 over square root 2. Now, if these two guys are 0, then it means what? Huh? Either A0 equal to 0 or B1 equal to 0 and A1 equal to 0 or B0 equal to 0, right? But if this is the case, if A0 equals to 0, then A0, B0 must equal to 0, right? A0 is 0. Then if I call this 1, 2, 3, 4, then 1 is wrong. Contradict, right? And similarly, if B1 equal to 0, then 4 is wrong. A1 equal to 0, then 4 is wrong, B0 is 0, 1 is wrong. So it cannot satisfy at the same time, right? So this is contradiction. And the only issue is I make the wrong assumption. That means they are entangled. This state is entangled. Okay? Okay, so we will stop here.